My name is Mina, and I'm an application specialist here at Scandidose. And I'm going to give you a brief introduction to our new improved software module, Delta 4 DVH Anatomy 2.0. So, the Delta 4 DVH Anatomy 2.0 is an algorithm-independent and accurate software that determines the delivered dose to the patient based on measurements done in the Delta 4 PT or the Delta 4 Phantom Plus. And I will show you some results of calculations and also explain briefly how it works. We have three sets of Delta 4 suite analysis tools. And we always start with measurement done in the Delta 4 Phantom. We measured the dose in two orthogonal planes, and we can thereby determine the dose to the target in hundreds of positions and also the extension or the limit of the dose. And this allows us to determine if we delivered the right dose and in the right place. For the pass and fail analysis, most physicists use gamma evaluation. And as long as we have good agreement between planned and measured dose, this works very well. But the method of gamma evaluation has some important limitations, such as treating all deviations with the same importance, and it does not differentiate between under or overdose or in which structure it occurs. So then we have the next level of tools, which is the Delta 4 DVH. And here we get an overlay of the structure geometrical position onto the phantom, and we can determine if we have an underdose or an overdose in a specific structure. However, to further analyze specific deviations and also interpret the results in a better way, we have our third level of tools, which is the anatomy. And here we actually get the transition of the dose in a phantom into the complex patient anatomy. So in the phantom, we get the clinical relevance by seeing each structure overlaid on the phantom. But in the patient anatomy, we also get the clinical significance because we can actually determine what this deviation means to the patient and to the treatment overall. So, why did we develop a new version of anatomy? Simply put, it is a more accurate dose calculation, and it also improved the resolution by calculating the base fluence map using a finer grid. Here's an example where we have a field with the MLC open, closed, open, closed. And at the top right, you can see a vertical profile of the field where the red solid line is the measured dose and the green dots represent the measurement in each diode. And as you can see, the agreement is quite good. We have a few deviations, but overall the agreement is good between planned and measured dose. And at the bottom, we see the dose reconstructed using the old software, the old anatomy. And as you can see, it does not reconstruct the dose accurately enough. But if we look at the calculation using Anatomy 2.0, we can see that the agreement is much better, and it also agrees much better with what we see at the top here. And more importantly, where we do see some deviations, these are also reconstructed in the bottom picture here. If we look at a more clinical example, we here have a case with a patient with a tumor in the head and neck region. And there's also some dose given to the lung. And in Anatomy 2.0, we have a lot better handling of low density regions, such as the lung here, where you can see at number 1, we have very good agreement between the planned and measured dose. And Anatomy 2.0 has also an improved handling of steep gradients, which is illustrated here at number 2. So we have better resolution, we have better handling of low density areas, and also better handling of steep gradients. Another example is from when a user measured underdose of an IMRT prostate plan due to not taking the treatment couch into account at the dose planning. So they see a distinct underdosage in the PTV, and the rectum dose, however, still agrees very well with the plan. So there's about a 1% underdose in this plan. If we look at the results from anatomy, and the DVH here, at the bottom you see the result from the old anatomy, and at the top with the new improved version. And as you can see at the bottom here, there's a general relative dose deviation as well as the distinct underdosage. And for the rectum dose, the agreement is not very good and the dose is not reconstructed properly. However, with the improved anatomy 2.0 at the top here, we do indeed see the distinct underdosage for the PTV, which is the red, and the rectum dose agrees very well, as expected. And here's another example of a VMAT treatment, a slightly more complex plan. And we have a low dose region in center field. And here we see two horizontal profiles of the two detector planes. And as you can see, there's very good agreement between delivered and measured dose. If we go on to the anatomy view of this, also looking at a horizontal profile, same as for the measurements, in the calculation here, we can see the good agreement, which is also verified here in the histogram, where we have a 0% median dose deviation. So now we've looked at some examples. How do we do this calculation? Well, we start by measuring the dose in the phantom. We then, for every control point, take information from the imported treatment plan and calculate the planned dose in the phantom using information such as MLC position and number of monitor units. We compare the measured and the delivered dose in the phantom and then calculate a dose deviation fluence map. So here everything has been done in the phantom, so we have high accuracy and we have good resolution. And we then take this dose deviation fluence map from the phantom and project it onto the patient. So now we can calculate the delivered dose or the delivered dose deviation in the patient anatomy. We import the treatment plan from the TPS and take the specific TPS dose, add the two together to get the delivered dose in the patient in the Anatomy 2.0 software module. So just to emphasize how this is algorithm independent and the accuracy of it, I will just use some visualizing. We have the TPS dose with the TPS accuracy. We measure the dose in the phantom, calculate the planned dose in the phantom, subtract to get the difference. So this is like a fluctuation of the difference between the measured and the planned dose. Calculate this difference onto the patient anatomy. And here it's important to keep in mind that this deviation is really small compared to the level of the planned dose. And then finally adding this fluctuation or dose modulation onto the planned dose to get the delivered dose. So what this really means is that we use the TPS dose with the TPS accuracy and just add a dose deviation, which is much smaller, about a magnitude smaller. And let's say that we did have a deviation between the two different algorithms that would be as high as 10%. And we would have a dose deviation of 10%, then the result in our calculation due to differences in accuracy in those algorithms would only be 1%. And in practice, we are talking about much less differences than that, and therefore also smaller deviations. So there we have our accurate and algorithm-independent software module, Anatomy 2.0. Thank you very much.